This is a little tutorial on U-substitution. Not only how to do it, but almost more importantly, when to use it. So let's take, for instance, a function that's just x to the fourth minus x cubed plus 2 that I'm integrating with respect to x. This is not worthy of any kind of U-substitution because for my function f of x, I know the antiderivative. So I just say, I take that integral symbol off. So I just say that my antiderivative is x to the fifth over 5 minus x to the fourth over 4 plus 2x plus Carl. And I'm done because I was given an integrand that was a function that I knew the antiderivative of. Same with sine x dx. I know the antiderivative of sine. I know the derivative of negative cosine is sine. So it's kind of, do I know the derivative of what gives me this function back? And the answer to this was yes, and the answer to this is yes. But sometimes we're given functions that we don't directly know the antiderivative of. For example, here's my function f of x, right here, this whole big chunk. And if I were to say the derivative of what gives you that, you'd get stuck because it's not readily apparent what the antiderivative is. What that means is at that point where you're like, I don't know, then what you do is you try to get it in the form of one you do know. And we do what we call U-substitution because we want to change it so that we have some function of u du, and this one is now readily recognizable. Maybe I can get it so I have u squared du, and I can write it as u cubed over 3. Or maybe I can get it so that it's cosine u, so that I can say that the antiderivative is sine. So what I do is, 9 times out of 10, I take the inside function, because if that was root u, or u to the 1/2, I know the antiderivative of it. So I let that be u. And sometimes what's helpful, until you get good at them, is take what you're going to have identified as your u and write it first, and then write the rest of the integrand. I didn't really do anything from here to here. It's the equivalent to saying 2 times 5 is psych, 5 times 2. But what it does is it helps you organize your work. So we write a u statement. We say, I'm going to let u equal my inside function, 2x to the 7th minus 3. Now, if I were to rewrite it, over here in green, if I were to just leave it at that and rewrite it, I'd have the integral of the square root u x to the 6th dx. And that doesn't make any sense. What I need to do is to get this as du, because we have to have a variable match right there. I can't do it yet. So then what I do is I take the derivative of u with respect to x. I power rule it. I bring the 7 out front. I knock the exponent down 1. The derivative of 3 is 0. So I really have that du is equal to 14 x to the 6th dx. My problem is the rest of this integrand isn't 14 x to the 6th d6th. I need it to get rid of the 14. So I do what I call a fraction correction, and I take 1/14. And this right here is just kind of my workspace where I'm trying to morph the integrand into something nice. So if I were to consider rewriting it, what I would have is I'd have the square root of my u, and the rest of this, x to the 6th d6, is really 1/14 du. Well, constants can come out front. So the 1/14 fraction correction ends up in front of the integral. And I have 1/14 the integral of the square root of u du. Now that is something I can integrate. I've got 1/14 the integral of u to the 1/2 du. And as long as there's that variable match, that would be like x to the 1/2 dx. We know how to do that. We add 1 to the power, disguised as 2/2. So it's going to be u to the 3/2. Then we divide by 3/2, which gives us a 2/3 out front. We also have the 1/14 fraction correction. We have Carl, and now we just need to clean this up. I end up on the bottom with a 2/14 times 3, or equivalently a 1/21, u to the 3/2 plus Carl. But u was defined as 2x to the 7th minus 3. So I back substituted in. And this is my function whose antiderivative is this one that I couldn't really tell at first. So again, the process is rewrite it, pick a u. U is almost always the inside function. I'm going to do one in a minute where it's not necessarily, but here's a trig one. Uh-oh. I don't know. I'm going to keep going here. If I were integrating sine of 8x dx, if I were to say, hey guys, the derivative of what is sine 8x? The problem is this. You couldn't say, oh, it's negative cosine, because the derivative of that would be sine 8x times 8. So that's not quite right. This is a function within a function, and that's usually a dead ringer or clue that you're going to use U-substitution. It is almost always the inside function. So I would say I'm going to let u equal 8x so that I'm doing sine u. But I need this to be du. So I say the derivative of u with respect to x is 8, or equivalently du dx equals 8. Equivalently, du equals 8 dx. But again, I just want dx, so I do a 1/8 fraction correction. I now replace this with a 1/8 du. So the rewrite of my integral becomes sine 8x, which is u, 1/8 du. Now I've got a function of u du, and it's a function I know the antiderivative of. Sine, cosine, negative cosine, sine. The antiderivative of sine is a negative cosine. So I would get the 1/8 out front, negative cosine u plus Carl. And now I back substitute. My u choice was 8x. So I plug it back in, and I say I have negative 1/8 cosine 8x plus c. If I wanted to check it, because a lot of times the checking process, no, I wouldn't do it really if I were you, but it does kind of help you see why it is the way it is. If I take the derivative of my answer, the derivative of my integral, I should get the original function back. Let's go do it. When I take the derivative of this with respect to 8, the constant stays out front. The derivative of cosine is negative sine times the derivative of the guts. The 8's cancel, and I get sine 8x. And if you go back up and look at the original problem I put up there, the original function was sine of 8x. So that's an example with a trig problem. Now I said that the u choice is almost always the inside function, but that again, what you're looking for is for your u choice, you want the derivative of your u to be the rest of the integrand or a multiple of the rest of the integrand. If on this one you say, I'm going to let u be 6x, well, du is 6. It's not sine, cosine, 6. I mean, you've got a whole bunch of unaccounted for stuff there. So I don't choose u to be 6x because it wouldn't be helpful. I'm just going to rewrite that because I accidentally erased it. So what I do is I've got two other options. I can either let u be the sine of 6x. Let's try it. Suppose I let u equal this whole thing. So I forgot my dx on the tail end of my integrand here. So if u is equal to the sine of 6x, then my du dx, my derivative of u with respect to x, the derivative of sine is cosine, the derivative of the guts is 6. So really what I have is that my du is 6 cosine 6x dx. Let's go see what I want it to be. I want it to be the rest of the integrand. I want it to be cosine 6x dx. So I'm going to do a 1/6 fraction correction. Now I'm ready. This box is just helping me change this into a function of u that I can easily integrate. Now if I am doing my integral, I've got u, right? And then I've got 1/6 du, but I bring the 1/6 out front of the integral. That is just like integrating x dx. It's x squared over 2. Well, this is u squared over 2. So I'd have 1/6 u squared over 2 plus Carl. That gives me 1/12 or u squared over 12 plus Carl. Now I go back and insert my original u choice. It's cosine, it was sine 6x. So this is sine 6x squared. Now it's the whole function squared, so you either need to put brackets around the entire thing or in here, but you can't put it just right out here on the outside. All over 12 plus Carl. And again, I want you to see this being checked because that's where you see the undoing of the chain rule in this process. So suppose I was going to check this. I would bring the 2 out front when I take the derivative and I'd get 2 sine 6x times the derivative of sine 6x, which would be cosine 6x, times the derivative of the inner guts, which is 6, all over 12. Carl goes to 0 when you take his derivative. This 2 and the 6 cancel, and it sends me right back to my original integrand. All right, one more, and then I think that'll be it for this little demonstration. Let's take and integrate one that looks fairly complicated, but once I u-sub it, won't be so bad. I've got 5 secant squared x on the top, and on the bottom I'm going to put a 2 root tan x dx. I'm going to do my number 1 rule with integration, which I always like to bring my constants out front. So I'm going to bring the 5/2 out front just to get it out of the way. I'm integrating secant squared x over the square root of tangent x dx. And if I were to ask you the derivative of what gives you this, you'd be going, da, ba, da, ba, da, ba, da. You don't know. So we're going to get it into something we do know. We're going to use U-substitution. We only have a couple options for our U. It could be secant. If U was secant, the derivative of U is secant tangent. It's not 1 over root tan x. See what I mean? I don't get the rest of the integrand. If I were to let U equal tangent x, my derivative would be secant squared x dx. That's where I kind of go score because that is the rest of the integrand. So I know that my choice, I only had two inside functions. It was either secant or tangent. Tangent was the winner because when I take the derivative of my u choice, when I take my du dx, the derivative of tangent is secant squared. Du dx is secant squared. So du is secant squared dx. Well, that's exactly what the rest of this integrand is. Really, what I have is, when I rewrite it, I don't even need a fraction correction. I've got the 5/2 I took out front. I've got root u on the bottom. And the whole rest of this is just du. And you can write it as du over or just go like that. That I can integrate. That's equivalent to 1 over root x dx, or x to the negative 1/2 dx. This is really over here, u to the negative 1/2 du. I add 1 to the exponent, disguised as 2 over 2, and I get u to the 1/2. I divide by 1/2, which has me multiply by the reciprocal. I have the 5/2 that I pulled out front of the integrand from the beginning, and I have Carl hanging on the end. Once that's all done, I clean up my fractions. I replace u with my original choice. Up here, it was tangent x. It's to the 1/2 power plus Carl. And again, I want to show you this being checked. If I did it right, when I take the derivative of my integral, it better give me the original function back. Let's do it. The 5 stays out front. I'd bring 1/2 out front. I'd do tangent x. I'd subtract 1, because again I'm doing a derivative. I'd multiply it by the derivative of the guts, which is secant squared x. The derivative of Carl is 0. What does that give me? On the top, I'd have the 5 and the secant squared x. On the bottom, I'd have the 2 and a root tan x. Notice that that's the original integrand. So hopefully that's helpful for you. These are kind of similar to some you're going to see on the test. You might want to run through this another time if you didn't get it. Have a good one, and thanks for trying, guys.